Hey guys, welcome back to video 5, and today we're going to look at the out-of-sample performance of the 6 portfolios we calculated. So far we've done a good job optimizing the portfolios given the sample period we're using, but we don't really know how they perform after that. So to analyze this, we're going to use the periods 2014 and 2014 to 2016. The first thing we're going to do here is copy the code that we had above that defined our sample return data. The only thing we need to do here is change the ending year and the beginning year to 2014 because that's the period we're looking at. And you also want to update the variable names, and there's no need to go through these calculations because the sample statistics are calculated the exact same way as we did in video 1 or 2. Now it's important to realize we aren't changing the weights of the portfolio from our sample period because our goal is to analyze the durability or robustness of the various portfolios' performance. Therefore, analyzing the performance is relatively easy because we're just multiplying the weights by the annualized mean and standard deviations of the portfolio. So we'll start by assigning a variable industry returns, and we just want to isolate the returns of the 47 industries. Again, subsetting from column 2 to the number of industries plus 1. Next, we want to combine the optimal weights into one vector. So we're going to assign a variable OPTW, and we're going to use the cbind function to combine the optimal weights. And we have WG, and the equally weighted portfolio is just a repetition of 1 divided by 47 times. And then we also have our weight from our M1 portfolio, our M2 portfolio, and our tangency portfolio. Finally, we're going to multiply these two matrices together, and we're going to call this MuVec4 for 2014. And we're going to use the as.matrix function to put the industry returns into a matrix that can be multiplied. And then we're going to multiply that by the optimal portfolio weights. And then finally, we're going to annualize the means of the portfolios and the standardized deviation. So we're going to assign a variable portfolio means 4. And we're going to again use the apply function, and we're going to use the vector of means that we just calculated. And we're going to sum it up by columns. We're going to take the average, and we're going to multiply it by the number of trading days per year. And we're also going to do it for the standard deviations of the portfolio. So we'll do PSD4, and again using the apply function, the mu vector, the column vector, and we're going to take the standard deviation, and again we're going to multiply it by the square root of n, or the number of trading days per year. Those were the only necessary calculations for this video. So now I've gone ahead and exported a table and created a plot for the 2014 performance. The process in doing this is exactly the same as we did in the previous videos, so it's a bit redundant to do it again. The rest of this video will focus on comparing the 3 tables and plots that we've created for our sample period, the 2014 period, and the 2014 through 2016 period. To start our analysis, let's compare our optimized portfolios to that of the market. And you can see that all the optimized portfolios, except for the tangency, on a risk-adjusted basis, have beaten the market. The tangency portfolio is likely performing so poorly because much of the optimization is dependent on the expected returns of the 47 industries, which can be highly biased. You can also see that the equally weighted portfolio in 2014 in the periods between 2014 and 16 also don't beat the optimized portfolio. So there's certainly some value add to optimizing your portfolios. This is the end of this video section on mathematical solutions to optimization. Our next set of videos is going to use quadratic programming to add additional constraints and improve the robustness of our model. I hope to see you there.